The chemistry of carbon. Carbon is the most abundant isotope that has 6 protons, 6 neutrons, and 6 electrons. It has 4 valence shell electrons. Here's a little picture showing the carbon bonds via its 4 valence electrons. It is very good at bonding to itself to form long chains and rings and other structures. It's important to know the definition of catenation, which is the ability of an element to bond to itself. Here are some carbon structures. You can see we have a linear chain. It can branch off, it can form a cube, it can cause simple rings or even rings that are fused together. The study of these carbon-based molecules is called organic chemistry. We have allotropes of carbon. Okay, you can see you got a diamond, you got a pencil, we get a simple pile of coal. As you can see, it's all carbon that is bound together. There are reasons for those physical differences that we just saw. The diamond has each carbon bonded to 4 others. Graphite in the pencil has each carbon bound to 3 others, where layers can slide over one another. We also have things like carbon nanotubes. These are thin, hollow cylinders made of carbon. They can be metals or semiconductors. We have a certain type of bonding in carbon allotropes. Each carbon wants 4 bonds. The options they have are as follows. They can do 4 single bonds, 2 single bonds and 1 double bond, or 1 single bond and 1 triple bond. Explain the error in each of the following molecules. Well, A, the bottom carbon only has 3 bonds. It needs to have 4, right? In B, the left carbon has 5 bonds. Well, it can't. It can only have 4. In C, the left carbon only has 3. 1, 2, 3, and it needs to have 4. Hydrocarbons are compounds made entirely of carbon and hydrogen. The majority of petroleum compounds, like when you get gasoline, propane, things like that. Carbon always forms 4 bonds. Hydrogen always forms 1 bond, so it works out well. Here's the example of petroleum, which is primarily used as fuel. It's used for many other products as well: fertilizers, insecticides, plastics, food, preservatives, paints, inks, lubricants, detergents, solvents, medicines, many different things. So petroleum is used a lot. The chains of carbon are the number of carbon atoms in the longest continuous chain. Here's a chain length of 8. We can also have a linear hydrocarbon. Each of the non-terminal carbons is attached to each other's carbon atoms. It doesn't form a straight line, since the bonding angle is 109.5. You can see these are all tetrahedrals here. We can also have a branched hydrocarbon. This is where at least 1 carbon atom is attached to more than 2 other carbon atoms. A small branch forming off of the main one. Sometimes we just use this, we do this with a line drawing. This is a representation that shows only carbon-carbon bonds and omits the hydrogens. You just assume they're there. Double and triple bonds are shown with multiple dashes. You can see a double bond here between these carbon atoms. Saturated hydrocarbons contain only single bonds and a maximum number of hydrogen atoms. Sometimes we have unsaturated hydrocarbons, which contain at least 1 double bond or triple bond and contain fewer hydrogen atoms. Here's an example of ethane with a single bond, ethene with a double bond, and ethyne with a triple bond. We've heard of saturated fat and unsaturated fat. Here's an example. A saturated fat has no double bonds, okay? An unsaturated fat, such as vegetable oil, has double bonds. Sometimes we talk about isomers. Isomers are compounds with the same formula but different structures. You can see here they have different boiling points based off their structure. We talked about the IUPAC nomenclature system. This is a standard naming system of chemical compounds. It becomes more complicated for organic compounds than for molecular ones. We got methane has 1 carbon, ethane has 2, propane has 3, butane has 4. We also name by the number of bonds present. An alkane is single bonds, alkene is double, alkyne is triple. Here are the number of carbons present in a main chain. So if the chain length is 1, it's meth, for example, methane. 2 is ethane, 3 propane, butane, pentane, hexane, heptane. Octane, nonane. So as you get a little bit higher or in the middle, starting with pentane, pentane's like pentagon, right? Hex is like hexagon. So those are pretty easy. But you also have to be familiar with the ones once you start getting up above 10. Okay? So you have to know and remember all of these. So when it comes to boiling points, the longer the alkane is, the higher the melting and boiling points are. So methane has a boiling point of negative 164. So that's pretty low, right? Icosane, look at this long chain. Huge boiling point, 343. We also have halogen functionalized hydrocarbons. This allows custom tailoring for a variety of applications. We have trichlorofluoromethane, which is Freon. Okay, you may have heard of that in your refrigerator. Then we have dichloro-difluoromethane. This is Freon 12, which is also a refrigerant. We have trichloromethane, that's used as like chloroform, and trichloroethane, which is dry cleaning fluid. This may be familiar to you guys. Teflon, non-stick coating. Very long chain. Okay, it keeps going. So far, we can't even fit it on this page. We also have alcohols that fall in this organic chemistry classification. Ethanol is something that's consumed in drinks like wine and beer, and these drinks are aqueous solutions. Sometimes we talk about absolute ethanol. That's 100% pure or 200 proof. And it's available pretty much only for research and industry. I think I have 100% ethanol in my refrigerator on campus that we used to use for a lab. But that's considered 200 proof. So when you buy something that's 80 proof vodka, it's not 100% pure. It's actually diluted. Denatured alcohol has poison added to it, which makes it undrinkable. So you wouldn't want to drink that. Next, we have ethers. These are used as organic solvents. Diethyl ether was once commonly used as an anesthetic, and they can be inflammable as well. Next, we have organic acids. These contain both a carbon-oxygen single bond and a carbon-oxygen double bond. A very common example of this is acetic acid. It likes to donate hydrogen atoms. It's very acidic. Then we have organic bases, which we call amines. These contain nitrogen atoms that can accept a hydrogen ion. We often have a sharp, unpleasant odor. You think of amine or amino, kind of smells like ammonia. If you've ever cleaned with that, it really stinks. Next, we have ketones and aldehydes. These contain carbonyl groups. Propanone is commonly used and is considered a nail polish remover. Ketones, aldehyde, acetone is what I use sometimes. Here's a summary of some of the organic compounds that we just went over. It's a nice little quick review.